Okay, an interesting topic would be to compare the dependency of the electric field on the distance away from the source for these different symmetries. We have studied three symmetries: spherical, cylindrical, and planar symmetry. We learned that for any spherical symmetrical charge distribution, the electric field should behave like 1 over r squared. R is the distance between the point of interest and the center of symmetry. So if you have a point or a finite size sphere, as you move away from it, okay, as you move away from it, you find that the electric field goes like 1 over r squared. That's how it decays. For a line, it goes like 1 over r, and for the plane, it doesn't decay at all. It doesn't decay at all. First of all, does it qualitatively make sense? Okay, does it qualitatively make sense? Well, think about it. If it's a point charge or it's a finite uniform sphere, then as you move away from it, the source looks smaller and smaller and smaller, right? So it should get weaker and weaker and weaker. So that's how it depends on r. It gets weaker by 1 over r squared. That's the Coulomb's law. But if it's a line charge, remember, it's an infinitely long line, okay? So even if you move away from it, the thing still looks infinitely long, right? It doesn't look any smaller. So therefore, it shouldn't decay as fast. So it decays like 1 over r. But the line, of course, is not as good as a plane. A plane is made of an infinite number of lines parallel to each other, so it's even better. How much better? It doesn't even decay at all. See, this goes like r to the power -2. This goes to r power -1, and here is r to the power 0. You see? That's how the dependency. That's how the dependency is. So qualitatively, it makes sense. Okay, but quantitatively, is it possible to use a simple argument to show that the electric field should behave like 1 over r squared for spherical distribution, 1 over r for cylindrical, and no r dependency for planar distribution, without all this calculation based on Gauss's law? We don't even want to use Gauss's law. Is there something simpler? If you want to use something even simpler, it's got to be more fundamental, okay? We go all the way back to Physics 1A. We go all the way back to the first chapter of Physics 1A, in fact. Where did we learn this very simple but very important principle? What it's called? Dimensional analysis, isn't it? Okay, for dimensional analysis, you know the Coulomb's law tells the electric field should go like charge is always charge times, you know, a constant k, that's always there, right? And you divide this by what? By some sort of length squared, okay? Some sort of length squared, so L squared. That is the electric field. The electric field should always behave like this, okay? That is the dimension of the electric field, no matter what. Now, in the case of a line, okay, suppose I have a line like this, right? I got a line like this. Should I use the total amount of charge Q if it's a uniformly charged line? Should I use the total amount of charge Q if the line is infinitely long, uniformly charged? What do you think total charge Q is? That would be infinity, right? It makes no sense, right, to use the total amount of charge. Therefore, for a line, I should be using charge per unit length instead of total charge, because that goes to infinity. So obviously, I should use lambda to replace Q. Lambda has a unit of charge over length, right? As a matter of fact, if you double lambda, everything else being the same, if you double lambda, then that's the same as increasing the charge, doubling the charge everywhere. Shouldn't E be doubled then? Okay, so that, in other words, for linear charge distribution, you know, if it's a cylindrical charge distribution, you know E should be proportional to lambda, okay? Because when you double lambda, you obviously double the electric field because you double the amount of charge everywhere. E is proportional to lambda. But lambda itself, again, has a unit of Q over L. Okay? So can you write lambda over r squared? You cannot, because lambda itself is already Q over length. Okay? So lambda over r squared is wrong in units because it will give you charge over length to the power 3, not over length to the power 2. So if it depends on lambda and r, and it's proportional lambda, then how should it depend on r? Well, to make dimensionally correct, must be lambda over r. That's the only possibility, right? Because then you get charge over length over another length. That's right. So you see, from simple dimensional analysis, we learn that for cylindrical charge distribution, the electric field should go like 1 over r. There's no other choice. Alright, now you can make a similar argument for planar symmetry. For planar symmetry, it is the only thing I should consider is not the, as far as the strength of the source is concerned, is not the total amount of charge, because again I have the infinitely large plane, uniformly charged, total amount of charge is infinity, right? So this time, what should I replace it with instead of Q? Well, I should replace it with what? With sigma, right? Charge per unit area. Okay, so E this time is proportional to sigma, and sigma is charge over area, which is charge over length squared dimensionally. So you see, if E is proportional to sigma, sigma already contains charge over length squared. Do you think I can stick an r somewhere into this expression without breaking the dimension? No, I cannot. Sigma already has the right unit. Alright? So therefore, r should not be anywhere in that equation because sigma already takes care of the units. So therefore, E should not depend on r. In other words, it's constant. Okay? Just like we saw here. There is no choice. We can get that directly from dimensional analysis. Okay, now, I have said before that there are other applications of Gauss's law. It goes beyond calculating the electric field for highly symmetrical charge distributions. Another area where Gauss's law becomes very powerful is when you apply it to so-called ideal conductors. Okay, ideal conductors. What's an ideal conductor? Okay, it's a conductor with zero resistance, so that you put a charge here. This charge, when it moves under the influence of the electric field, there is nothing to stop it. It keeps on moving. Okay, it keeps on moving. So, one of the things that I can say about ideal conductors is that the electric field everywhere inside must be zero. Okay? Because if the field were not equal to zero, say there's a field here at this point, what's going to happen? It's going to drive the charges. Okay, the charge will then start to move. If the positive charges, they go this way along the electric field. If it's negative charge, they go that way against the electric field. Okay, a regular piece of metal is not an ideal conductor, but is an excellent approximation to an ideal conductor. In that piece of metal, there are so many what's called free electrons. They're free to move. Okay, they are not bound to any particular atom. Rather, they swim around. They're free to move with very little resistance. So if there were an electric field anywhere inside that metal pointing this way, it's going to cause the electrons in that region to go backwards, the free electrons. And as the electrons move, they will go to different locations. Therefore, they're going to reshape the electric field until what? The electric field goes to zero everywhere inside, and that's when the motion of electrons stop. Okay, so for an ideal conductor, it is clear that the electric field anywhere inside must be zero. Okay, must be zero. This has nothing to do with Gauss's law. It's just a requirement for the system to have an ideal, to be ideal. There is no resistance. But when we combine the requirement of Gauss's law and the requirement of ideal conductor, that is E equal to zero inside, we will be able to find interesting results regardless of any symmetry consideration. Okay, so what are the interesting results we can find? First of all, an ideal conductor may or may not be charged. If it's not charged, we say it's charge neutral. In other words, the amount of positive charge cancels the amount of negative charge. But I can also put some charge on it. Okay, I can put some charge on it, and let's say we put some charge on it. So here's an ideal conductor. I put some positive charge on it. Okay, so there is a certain amount of excess positive charge. My first question is, where are these excess charge located? Okay, is it possible for the excess charge to be somewhere inside, in the interior of the conductor? Well, intuitively, you know that's probably not going to be the case, because suppose we have these positive charges, right? They don't like each other, do they? So they're going to fly apart, right? They're going to fly apart because they repel each other. So they try to move. Okay, being an ideal conductor, these charges will experience no resistance to keep on moving until what? They're being stopped by the boundary of the conductor. They got no place to go, so where do they end up? Well, they end up on the surface of the conductor, right? But that's just an intuitive thought. How do we show for sure that all the excess charge must live only on the outer surface? It cannot live anywhere in the interior. Well, it turns out we can get that from Gauss's law. Suppose there were a single positive charge here in the region, in this particular region. What I'm going to do is I'm going to draw a Gaussian surface to surround it. Okay, so imagine there's a Gaussian surface like this. Now, what is the flux through this Gaussian surface? Remember, this entire Gaussian surface is within the plane. Is within the body of the ideal conductor. And within the body of the ideal conductor, what is the electric field equal to? Well, it's equal to 0, right? So, what is the electric flux through this arbitrary Gaussian surface? Well, it's 0 because the electric field is 0, okay? Everywhere on the surface. So the flux is equal to 0. Flux equals 0. But wait a second. Flux should be equal to Q enclosed over epsilon naught. Okay, so what does that tell you about Q enclosed? What is that charge equal to? Q enclosed. 0. You know, you can draw a Gaussian surface everywhere inside. You can show that everywhere inside, you know, whatever region you pick, the net charge must be 0. So if there's any net charge, there is only one place to go, and that is the outer surface. Okay, it cannot live anywhere inside because of the combination of the requirements of Gauss's law and the ideal conductor. So that's the first neat application I get for the ideal gas law based on Gauss's law, for the ideal conductor based on Gauss's law. Now, the second neat application. Now that we know any excess charge must live on the surface, on the surface. Inside the surface, right inside, this is inside the conductor. Right inside the conductor, we know the electric field is 0. But what about right outside the conductor? Well, outside the conductor, there is no electrons to move around, so the electric field does not have to be 0. Okay, so my question is, what is the E surface? That is the electric field right outside the conductor, say at this point right here. Okay, the conductor can have any shape. It doesn't have to be, you know, any type of symmetry. Okay, the first thing I conclude is that if there is an electric field, this electric field must be perpendicular to the local surface of the conductor. It cannot point this way or that way. How do I know that? Well, because if the field points this way, it means it must have a component that is parallel to the surface, right? But if it's got a component that's parallel to the surface, shouldn't it then move these charges around? Because these charges experience no resistance, so they can then move around. After they stop moving around, it must mean that there is no component of the electric field along the surface. Everything must be perpendicular to the surface. Of course, these charges cannot fly out of the surface, so therefore, even if you have a field like that, they're going to stay put. Okay, so that's the first thing, is perpendicular. Perpendicular, and there is no field inside. That's the first observation. Now, let's try to figure out the strength, the magnitude of this field. We know the direction already. What's the magnitude? Well, the surface itself can have a complicated contour, but I just want to know locally, for this particular location, where is the electric field. So what I'm going to do is, imagine I'm going to amplify, okay, I'm going to amplify the surface, take a magnifier, magnify it, and then I'm going to take a small surface. Okay, I'm going to take a small region. Look at the small region here. I'm going to draw a Gaussian cylinder like this. Okay, a Gaussian cylinder. Because the region is very small, you can imagine the electric field is pretty much uniform. Okay, pretty much uniform throughout this very small region. Here is the top surface of the Gaussian cylinder, which is outside the ideal conductor. And here's the bottom surface, which is inside. So the bottom surface equals 0. Okay, because that's inside. And I'm not going to worry about the side, because the side is, the way I draw it, the side is perpendicular to the surface, and the electric field, as you know, is always either 0 or perpendicular to the surface, so nothing goes through the side. Okay, so for this little Gaussian cylinder, the only surface of that cylinder in which there is an electric flux is the top surface, outside the conductor. If the area is A, okay, the top area is A, what is the flux equal to? Well, you got a uniform field perpendicular to the area, so shouldn't the flux be equal to E times A, right? But on the other hand, according to Gauss's law, the flux should equal to Q enclosed over epsilon naught, right? And Q enclosed is the charge enclosed by this region. Okay, now remember, this is a cylinder, so this area and that area are the same, okay? And that area is also A, and the surface, if the surface charge density is sigma, how much charge is enclosed? That should be sigma times the same area A, right? So that should be equal to sigma A over epsilon naught. You can then easily solve for the electric field. A and A cancels, you got E equals to sigma over epsilon naught. You see how simple that is? See how simple that is? I have obtained the electric field right outside an ideal conductor, regardless of the shape and size of the conductor. The only thing you have to tell me is what is the local value of sigma. What is the surface charge density, sigma? You tell me that, you divide it by epsilon naught, you get the electric field. Okay, here's the magnitude, the direction is perpendicular to the surface. Now, if you recall, this result is kind of similar to the case of infinitely large plane. See here? That was equal to sigma over 2 epsilon naught. And strangely enough, there is a 2 here, and that 2 is missing there. Now, first of all, these are not the same thing, okay? This is an ideal conductor, so that on that side, there is an electric field. On this side, inside the ideal conductor, there is no electric field. In this case, we get electric fields both ways, up and down. So it's not quite the same thing. Okay, but it turns out that this case is related to the previous case of infinitely large plane, and we're going to elaborate that a little bit later. Alright, now you notice that I did not show you how to calculate sigma. That is a totally different story. If we're looking at a uniform object, such as a uniform sphere, then sigma should be the same throughout the surface because of the symmetry. But if I look at a complicated object, say a rod or a donut, whatever, sigma could be different from place to place. Okay, if I don't know what sigma is, I don't know how to calculate E. So you have to tell me how to calculate sigma, because without that, I do not know how to calculate E. But the calculation of sigma can be complicated. That is a totally different matter. We're going to discuss qualitatively how to calculate sigma in the next chapter. Okay, but at least once you know sigma, you know how to find E. Okay, now that we discussed the two major types of applications of Gauss's law, one is for systems of high degree of symmetry, and the other one is for ideal conductors. We're going to take a look at some further examples. But actually, before we do that, we have some loose ends to tighten. You know, we have concluded that for an ideal conductor with excessive charge, the charge must live on the surface. But what if, what if the conductor has an interior surface as well? In other words, it's got a hole. It's got a hole. Now, this is something we have to consider. So here's the conductor. This is the conductor. There's a hole. Okay, there's a hole. Now put some charge on it. We know the charge cannot live in the body. Okay, it must live on the surface. But my question is, here's the interior surface, here's the exterior surface. Can any charge appear on the interior surface? Okay, now that's something we haven't considered yet. So let's see how we might discuss that. First of all, if any charge were to appear on the interior surface, say a certain amount of positive charge, somewhere here, from Gauss's law, I can show you first that there must be an equal amount of negative charge on the same surface somewhere else, so that the total charge on the interior surface goes to 0. Okay, I must conclude that first. And why is that? Well, again, the magic law that we use to prove that is what? Is Gauss's law, of course. Okay, let us draw a Gaussian surface like this. Okay, now look, this Gaussian surface is entirely within the metal, within the body of the ideal conductor. So what is the electric field equal to everywhere on the surface? No, that would be 0, right? That would be 0. Okay, so if the electric field is 0, then what is the electric flux? Well, that is of course necessarily 0. But wait a second, the electric flux is proportional to the total amount of charge enclosed, and the flux is 0. So how much total charge is enclosed? 0. Okay, there's no question about it. It's got to be 0. So that's the first step. I showed that if you got some positive charge here somewhere on the interior surface, there must be some negative charge somewhere else. Okay, so that's the first step. And the second step, I want to show you that not only is the net charge equal to 0, there cannot be any charge anywhere, period, on the interior surface. In other words, no positive charge, no negative charge. Of course, the net charge is 0. How do I show that? Well, that's a little bit trickier, but if you have the right idea, it's not that hard. Suppose you have a positive charge, then necessarily we must have a negative charge somewhere else on the surface, something we just proved. And you can imagine the electric field line. Electric field lines always start from positive charge. They always end at a negative charge, right? So imagine there is an electric field line like this, okay? Then the electric field line like this. Somewhere from positive charge ends up somewhere in a negative charge. Now, what if I insert a small positive test charge here, okay? Here. This small positive test charge will then experience a force, right? The force is along the direction of the electric field. It goes from here to there, being accelerated. So by the time it moves from here to there, through the cavity interior, it's going to go faster. It will acquire some kinetic energy, right? Because it's being pushed by the electric field from here to there, right? Now, it's going to appear here after some time. What I'm going to do now, imagine, is I'm going to dig a tunnel, okay? I am going to dig a tunnel from here to there. Okay, it's empty. It's a very thin but empty tunnel. Now, once this charge starts from here, ends up there, it's moving pretty fast because it's been pushed by the electric field. And then as it enters into the tunnel, this tunnel is dug inside the metal, therefore there's no electric field anywhere inside the tunnel. So once this charge enters the tunnel, it experiences no electric force, okay? But it's going to move so that there's no force acting on it except the force that the normal force that pushes it along that forces it to stay inside the tunnel. So it's going to keep on moving at the same speed, right? So we neglect friction. It keeps on going at the same speed, and it's going to reappear here. All right. By the time it reaches here, it will once again enter this electric field. It will be accelerated one more time. So by the time it gets there, even faster, and then keep the same speed, and then even faster, keep the same speed, even faster. So you see, every time it goes in a cycle like this, it gains more kinetic energy. It goes faster and faster and faster. What do you think we just invented? Well, we invented a perpetual motion machine. We got free energy. We just solved the world's energy crisis, didn't we? Right? This this positive charge particle starts from here. With every cyclic move, it goes faster and faster and faster and faster. Where does the energy come from? Is that possible? Well, I wish it were, because that would give us free energy, but of course, no free lunch. Okay, this is not possible. What was wrong? You cannot have a positive charge here and negative charge there. Otherwise, you get free energy. That violates the conservation of energy. Doesn't work that way. Okay, so we conclude that even if you had an interior surface, okay, even if you had an interior surface, all excessive charges can only live on the exterior surface. Nothing is on the interior surface. Nothing. Okay, that is an extension of the conclusion of where the excessive charge would be based on Gauss's law.